Right.
Okay, so myself is Nachiketa Acharya. I am basically a statistical climatologist, working almost 10 to 12 years in climate analysis, mostly focusing on S2S prediction and verification. Recently, I just joined Penn State, but before that, I was at International Research Institute, where my main responsibility is actually in this ensemble forecasting, verification, this and that. So that's kind of a nutshell, and already we have a bio, so people can look at that. So on that note, as I have to cover so much, so I'm sorry to being a little rude, uh, uh, to just stop the discussion. So today, like for this, we'll discussion about the ensemble forecasting system, which make the probabilistic forecast in different scale, whether it's a weather forecast or it's a sub-seasonal forecast or it's a seasonal forecast. But in general, the verification system is kind of same. So we'll discuss on that and just have this cartoon in the first slide. I want to just, whoever don't have much experience or knowledge about what is ensemble system look like, is kind of a, very interesting plot that you actually a bunch of different forecasts, which is very less different when they start, but at the end they have a huge difference. So on that I will start, but before that, just a quick, like, what are the topics we should we'll cover today, like the introduction of ensemble forecasting system, especially like how we can calculate the probability from the ensemble. And then we kind of distribute the talk into two different aspects. One is how to verify the ensemble's prediction to have a reliable or good forecast. Second, once we have the forecast from the ensemble, how we actually measure the accuracy and the skill of the probabilistic forecast. On that note, to start with again, what I'm already started in the first slide, like how the ensemble forecast look like. So basically, if we kind of generalize the system or dynamical model in different scale, like instead of having one forecast, uh, we should have a more forecast. The reason behind that, because the system, which is that the atmosphere is so complex and non-linear, we don't have the confidence of one single realization of our forecast. So that, and also like having a one forecast does not give us an opportunity to verify the uncertainty of the forecast. Instead of that, if we have like a multiple forecast, then we should have like a probability of any events instead of just one value. So basically it start with the one distribution, one system, and then to change a little bit of the conditions, it might be an initial condition problem if it is the weather forecast. For the seasonal, it's initial condition and the boundary forcing, because the seasonal scale, ENSO is one of the biggest drivers. So depending on the ENSO situation, people run the models. So generally, like with a different initialization and different boundary condition in a dynamical model, we are ended up with a different kind of forecast. It's very interesting. You start with a one PDF or probability distribution function, but at the end you will have a different kind of probability distribution function. So that's in general the ensemble forecast. Now, like for example, if you want to look how it looks in real time, so that's a very recent example of Nino 3.4 forecast of this month initial condition. I just took one model as an example, which is CCSM4 in NCAR. If you look, like the black line is what was observed up to now in terms of Nino 3.4, but using the May month initial conditions, you can have a different forecast. So if you look at the initially, like those ensemble members behave very similar, but after the time, like certain time in the lead, you can say there's a bigger spread or standard deviation or variance among them. The bolder line is a mean of whole distributions, whole members. So you can see like this kind of giving you that the signal of the system, and these are the spread. We can actually discuss more in upcoming slide what is signal, what is spread, but this is like a one example. And again, this is another example, but with so many different models. So each model have different members, so you can look like is like a spaghetti maps here, but the solid bold lines are actually the mean of the system or the signal of the system. So that's kind of, in real time how this ensemble looks. Now the question is like, okay, so we have an ensemble, but how to make the probability? Like how the atmospheric scientists make the probability? It has a two different approach. Obviously, non-parametric is kind of very popular, and also there is a parametric approach. Again, I just go quickly on that, like what is non-parametric when you talk about probability. So it's a kind of a simple classical probability theorem, like number of favorable cases by total number of cases. For example, like if you know like what is your end product, for example, you want to predict for three different forecasts, below, near, above, or you want to predict a forecast greater than temperature, let's say 25 degrees Celsius. It depends like how you make your category. Based on that, you can actually simply count. Suppose you have 10 members. How many members is actually following that events, and then divided with the total number. One example in a quantitative way, this is a good example. If you look at that probability distribution function of that red lines, suppose this is your climate look likes, and these breaks are in different category. Let's say the first break is like less than equals to everything is below, and in the between the two breaks is near normal, and the other one is above normal. Suppose we have those forecasts, which is that black lines, straight black lines, and you can actually calculate the same way we explain in this formula. Like for this, in this category, you can see only 3 members out of 81. In the near normal is 11 members, and then the other one is 67 members. So at the end, you can actually calculate the probability. So this is an example of probability of above normal. So it's 67 by 81, which is, obviously it's more because most of the members on that side. So that's in general, in practical, people can calculate the probability from the ensemble members. I also mentioned about the parametric approach, which is a little bit of complicated, and obviously this is not this is beyond of this discussion, but I just want to mention like how we can calculate the parametric weight of probability. On that case, like the mean of the member, we assume that's the mean of the probabilistic forecast distribution. In this map, you can see that the blue line is like a climatological PDF. And suppose the red line is the PDF of the forecast coming from the ensemble system, and the mean is actually the vertical line, the vertical lines, which is actually the mean of the all members. Now the question is like how we calculate the spread, or how to calculate the standard deviation of the distribution. It is a bigger discussion. It has 3 different approach, but just one quick comment, like mostly people use the ensemble spread, which is the standard deviation among the members. Anyway, so that's why people can calculate probability. So now we have actually 2 PDF. So we start with the prior knowledge, which is equal probability of 3 category, which is 1/3 of each. But suppose now we have a new distribution look like this red PDF, and then our prior assumption is going to be updated. For example, if we just see the intersection part of this below normal category from the climatology and the forecast from the GCM, you can see that is like 2% of the area. So from the 33% comes down to 2%. Same thing for the normal, and same thing for the abnormal. So you can see like, when you talk about the signals and noise and, changing the probability, so it's actually, you can see in that way, so how the climatological forecast changing based on the ensemble system. So on that note, it's kind of explain that how to make the probability from the ensemble members. On that note, coming to our main topic, one of the main topic is like ensemble prediction verification. So question is like, what are the question we actually trying to ask when you have that ensemble prediction verification? The basic assumption to have a different kind of forecast, because we are thinking about that not one forecast is enough to statistically, same as the focus, same as the observation. That's what we need a more. So the question is like, do the observation statistically belongs to the distribution of the ensembles? Then what is the utility of this system? And the next question is like the predictability, how, like from where the predictability comes, or from where the predictability don't come. Like for example, if you say that this model is bad or this model is good, the question is like, the good or bad depends on like how they actually address the predictability question inside the ensemble system. On that, I started with again the same diagram, like, here we can also plot the observation. So the assumption is like, you see like so many forecast. So observation is one of them. That means like observation should behave like one of the ensemble members. That's the whole assumption of the ensemble system. But if you look this example uh, in a little bit of different times frame, you see like the observation look like outliers. That means this whole ensemble system does not cover the observation. So it's all depends like in which slice you're looking at. On that note, we can actually quantify these things, the assumption, whether the observation have the same statistical properties from the ensemble members. So Hamill in 2001, he like in this paper, he actually explained about this telegram or rank histogram. So basically what happened, like, for example, if you have a 6 forecast from 6 ensemble members, you just rank them. And you also have the observation to verify, and then you find like where the observation falls on that ranks. In other way, like if you have a 6 forecast, you can have a 7 bins, right? Because you kind of make the sorting way. So from 0 to 10, 10 to 20, 20, 30, like if you have a different class intervals of the forecast, and then you can find like in which bins your observation falls. So one example of this, like for example, this first figure, the blue one is observation. So we can say that is the first of the all 21 members. The second one is like around 14 of this member. So that's the way you can check that whether your ensemble system actually cover that spread where the observation should come from. So that's called the rank histogram. But question is like how we make a decision based on that rank histogram. What should be the ideal? The ideal look like when the observation is indistinguishable. For example, suppose we have 20 members in this example and we have 21 bins. So almost every bins the observation falls. That's why it look like very flat. But it's not the obvious case for everything. Like for example, if you look at the right one, it depends. Like for this particular example, most of the cases the observation falls out of the range, out of the 21. That's what you see, like that if you look at that bar diagram or histogram, it is very high in 2 borders. That means the number of cases when the observation did not fall and that bins, it's actually more. So that's in a different way we can actually look the ensemble system. But rank histogram mostly giving us an idea like how flat of our rank histogram based on how many times the observation actually falls within the ensemble spread. And based on the flatness, we can actually conclude the system whether it's a negatively biased or positive bias or over dispersed or under dispersed. So again, I don't want to spend more time on that. It has like you can put the reference afterwards, so you can look like how this can be calculated, how this can be concluded. But the basic assumption is like, as I said, like the observation should behave like one of the ensemble members of the system. Now the question is whether it is the only necessary and sufficient condition for that. But it's not, because a rank histogram does not give us an idea about the sharpness. And what is the sharpness? We'll again discuss more later. But the sharpness is like the probability. Like, for example, of an incident, a probability is 30% if some ensemble give us, and one ensemble give us a probability 70%. So which one is sharp? Obviously, the 70% is sharp, because when you're closer to 100% or you're closer to 0%, you're more confident. So that rank histogram did not give us that kind of information from the ensemble system whether this probability is sharp or not. So in that sense, we need to look in a different aspect, where you call spread skill relationship. So now the spread is important from the rank histogram. At the same time, the skills is also important, because whether our probability from the system is capture the incident happen. And that, because if our focus is sharp, is always have a more chances to get the observation correctly. On that note, like how we calculate the spread and skill. Mostly the papers, they said like spread is mostly the standard deviation among the members. And the skill is the difference between the signals, which is, you can say the ensemble mean, and the truth, in this case, observation. So things like if you have a large ensemble spread, that you have like less predictable events. If you have a small ensemble spread, you have more predictable events. And we can actually quantify this assumption in terms of a very simple scatter diagram. Like this is the ideal case from the paper in 1998, like how should it look like? But this is like some of the real-time example I brought it here. Like from the first, you can see like x-axis is the spread and y-axis is the error, mean square error of ensemble mean of the observation. And it should look like, kind of a diagonal line, but not exactly. But in this system, it's like only 0.3. And this system 0.4, this system 0.7. So if you compare these three different ensemble system with this particular spread skill relationship, you can have a conclusion that the last one is actually more like predictable in terms of how that ensemble members is created. So that means like the ensemble spread and the skill, the ensemble spread is actually representative of the skill of these things. So that another way to look at that, the ensemble spread and the skill. Now the question is like we talk about kind of using the same already, that signal and the noises. So if you're thinking about a frequency, we know like what's the signal and what is the noise. If you're thinking about a transistor, like if you're setting a FM station in your car, and sometimes it started with the like automatic search, and it goes different signal to find out, and you can say that different noise, and suddenly it's just choose. So the same kind of concept we can use here. Like again, the signal means what is like the main forecast, or like the predictable signal from your system, and the noise is obviously that ensemble spread. So we can actually think about in a two different component. One is external component and internal component, and the ratio between this external and internal we can call the signal to noise. The external component treated as the ensemble mean of all the members, and the internal component, obviously the interdeviation or variance within the inter members. We can also like mathematically you can actually say like the variance of the ensemble mean is the signal, and the variance of ensemble member is the noise. And again, if you look like how we can actually use that kind of verification metrics like two different system. If you look in these two example, like the first example, it has a large signal to noise ratio because if you look the ensemble spread or the standard deviation of the member, it's very less, because it's very confident about what the focus should be, and that's what the mean is kind of representing the central tendency of the whole system. But for the other cases, if you look that after a certain day times of the forecast, the members are very different each other. So that means it has a very small signal to noise ratio, because the noise are more, the signal is less. So you can use that idea to again compare the ensemble system in different two models. On that note, another concept is called potential predictability or signal to total ratio. Again, the assumption is exactly same. Like the assumption is like the observation should be behave like one of the ensemble members, and ensemble member should be interchangeable. So that means in terms of correlation, so like the correlation between the signal, which is your ensemble mean, and the true, which is observation, should be high and should be behave like same as the correlation between any of the ensemble members and the mean. So basically, like, if you calculate the correlation between any members and a mean, should be equal to the ensemble mean of the observation. And obviously that correlation should be high if you have a more signal. So one example I can show you in this Indian monsoon respect, like the left plots is actually, we have like, for example, we have a system which has like, 6 members, and like we just calculate the correlation between each member and the ensemble mean, which look like very strong. But when you calculate the same thing, like for example, you calculate the ensemble members and the observations, the correlations, it look different. So that means they are more like kind of this whole forecast system, uh, that the mean is very close to the ensemble members, but it's far from the real truth. Like if you're thinking about the rank histogram concept, like observation may be outliers from the whole system. So that's what, like the system itself, the ensemble system itself, have a good correlation between the members and the mean, but it's not the case in the observation, because observation is kind of out of the in the whole limit. So that another way you can actually compare that predictability or potential predictability for the members. On that note, now we are going to the next steps, which is the verification of the actual probability. So up to now we discuss about uh, that kind of find it, like kind of a measure how to find like whether the utility of the ensemble system is okay or not. That means like wherever the way their whole system designed for some models, whether those ensembles is actually responsible to bring the bring the perfect or good skill from the probability. Now we are thinking about, okay, so after that, suppose we have the probabilities. Now, how can we actually quantify the skill of the probability itself, which is coming from the ensemble system? And we can look in a different various way. We can look at the accuracy scale, like how close it is the incident happen or not. We can see the reliability. Reliability means like how can you reliable, like what's the like if somebody wants to use your forecast, like how much he can has a reliability on that forecast system. It's like kind of trust on the forecast based on his you know his skill in the past events. I can explain more on that. Another concept comes the resolution. So resolution means like how often that forecast is actually differ when the different kind of events. For example, like when you give the probability of 80% of a rain, whether the above rainfall or the flood like incident happen or not. When you give the 20% of the probability of rain, whether the event close to the drought or less. That's kind of things we can actually measure from the resolution. Another thing is sharpness. We already talked about a little bit. Like sharpness means like how sharp is the probability, whether you are giving the probability around 30 to 40% every time, or you are giving the probability either like more than 80% or less than 20%. That's another way to calculate. And the skill actually comes in the way like whether this forecast system is better than any reference forecast or not. I will come on that. And the last one, we'll actually discuss the discrimination, which is actually kind of Ian already discussed about in the contingency table, like how like uh, how can like forecasts are different from the when the outputs are different. We can actually come on that, but let's start with one by one. It comes to the accuracy first. So I'm sure like already in the previous discussion you talked about like the root mean square error or mean square error in the deterministic scale. But what about like you want to calculate this kind of same mean square error in the probabilistic space? So what should be the formula and how can we calculate? It's very simple. It's like the probability issued from an ensemble system and whether the observation happened or not. If I can just quantify, just give a sense like how we can look at, for example, this is a table of the rain and no rain in, let's say, in day one forecast, and you have a set of probability and you also have a set of observed rain or not. So then you can actually change this system in a dichotomous time series, like 0 means no rain and 1 means rain. Now we can just replace this formula with these values. So pi is actually the probability of here, and y, either it should be 0 or 1. It also depends on, like, for this, if you're talking about, we're just thinking about whether rain or not. But if you're talking about in a different categories, for example, above normal, below normal, near normal, or different different threshold, it can actually calculate independently for each thresholds. So obviously that difference should be 0 if or we have a good focus system, and the difference more if the probability is far different from what happened. And that is why the sharpness is so important, because why, like what is the observed frequency is like either 0 or 100% or 1. It cannot have like 0.3 or 0.5 because it's simply dichotomous time series. So that's what the probability value, if it is sharp, is very important. At the same time, it should have some kind of reliability. We can talk about that more. So on that note, if we can actually decompose this Brier score, we ended up with three terms. And each of every terms have huge importance in terms of how we look at it, look at the whole system. The first term is reliability. Again, the reliability means like, for example, you issued a forecast in last 10 days and you have the observation, and now we can actually try to plot those. So how many times you forecast, let's say you forecast some event 50% and it happened 50%, or how many times you give the forecast 20%, it's actually happened 20%. So that means you're actually, this forecast system is actually able to find out the observed frequency. So that's kind of reliability. Now the question is resolution, and resolution and sharpness is kind of very related, because the resolution means, like, as I explained earlier, like whenever you give the probability of something, let's say very high probability like 80% or 70%, whether the incident happened or not, or you give a simple probability like, let's say 30% or 33%, whether the rainfall is in the normal category. So basically, in other words, like whether your forecast has the ability to find it out whenever, by kind of distinguish the situation with distinctly different frequency of the occurrence. And the other part is the uncertainty, which is not like nothing to do with focus utility or focus quality, is actually mostly the variability of the system itself, or the variability of the observation. So that is why, as the uncertainty part including in the Brier score, so it should not be compared in different samples. That means, like, suppose you have a 10 days forecast of some weather forecast, and you calculate the Brier score. Now you have another model and you have only 5 days forecast. You can't actually calculate because of this uncertainty part, because the uncertainty comes from the variability of the observation. That's what you need, a kind of equal samples to compare different Brier score for different models. On that note, again, if you just simplify the concept, like the reliability is like, again, the forecast probability versus observed relative frequency. The resolution is like ability to issue the forecast close to 0 to 100% when the observation happened that way, and the uncertainty is a variance. So Brier score is a combination, or linear combination of these three terms. So now we talk about Brier score. So now we talk about Brier skill score. And whenever the skill score comes, that means like whether your system, your focus is better than the other focus or not. And most of the cases, we talk about a kind of a reference forecast, and it's come from the climatology. Again, like if you look at the first example in the cartoon where it show like different PDFs, the assumption of the climatological forecast for three different categories is equal, which is 1/3, 1/3, 1/3. That means like if you don't have any forecast from the models, you still have like a probability, and that probability is equally mutually consistent. That means like equal probability. Now, if you compare your forecast come from a climate model and compare with the equal probability, whether your climate model forecast is better than that equal probability or not. So that's the way we actually calculate the skill in this probabilistic framework. So we always need a reference. We can also change the reference from the climatology to a different model. For example, some system, where the forecast or climate forecast system has some model already, they have. Now they adopted with a new system. So they can actually compare the forecast between this old system and new system, depending on, and putting that old system as a reference. So basically, like, it's if it have positive skill, because that the way the formula looks like 1 minus some ratio. So if it is positive is better, it's negative is worse than the reference. So that's the way the Brier skill score calculated. Now the question is, like, before going to the other like RPSs or other things, because if you go back a little bit, like when you decompose the Brier score, we found a term called reliability. So we can actually plot that term on the Brier score in terms of attribute diagram or reliability diagram. So it's a kind of very simple idea, like taking all the cases in which the event is predicted to occur with a probability of, let's say, X%, and that event should occur exactly X% of those cases. Like, again, if I just simply go this example, and I'm sure like, next tomorrow, Kai will like cover this concept more. I just give one example. Like suppose we are kind of verify this one of the focus system, like how often the probability of temperature is greater than 25 degrees Celsius. And we kind of, you know, club all the forecast, and for this kind of system we need a lots of data. So that means, like, for example, you're thinking about a spatial verification system. Suppose you have like, let's say 18 to 80 grid points, and let's say you have like 34 years. You can actually take all the cases in a one and make a one vector and calculate this thing. You can't calculate for each grid, because when you calculate each grid, you have a very less number of samples. You need a more samples to have this kind of, reliability diagram. So it's kind of, you calculate like your, for each forecast probability, how many times it happened, and also you compare with how many times it's happened in the observed frequency. I can, if I just go next slide, it kind of look like this. So the diagonal line is like, or the 45-degree line is the line whenever is like kind of, perfect forecast. That means like whatever the forecast probability you actually issued is actually happen the same number or same percentage happen in the observed frequency. So that means like we need lines which is more close to the diagonal. So that means reliability is actually calculating this, like how close is our this line to the diagonal. We can also see the resolution of from the same diagram. The resolution again, like how far your probability from the climatological probability. So again, the sharpness things come, like how far is, like how sharp is your probability, how much, like whether you're always giving the probability like 30%, 40%, or 35% when your climatology is 1/3, or you're giving the probability like 60% or 70%, which is, how far, like it's far from your horizontal line. So from the same diagram, we can actually calculate the reliability. You can see the reliability and resolution. If I just again, kind of little bit more about Bryce skill score and the reliability, it's look like this. So we should have a, like we from this diagram, we have an area where the resolution is greater than reliability. We can see like, maybe we don't get the perfect reliable, but we get a area where you can have some kind of skill of the forecast. But we also have like, the climatological line. That means if your line is kind of close to the climatology, that means you don't have much resolution. So obviously, you don't have much skill of the forecast. So this is like a different diagram. Again, like tomorrow you'll see more and more, but I just want to give kind of explanation like how it look like. Like in the middle, you see like kind of perfect model, because this lines is very close to the, that red line. You can't see the blue line, but in the left and the right, you can see a example of the overconfident and underconfident. Now, question is like how it's over or underconfident. If you look about the x-axis and y-axis, these are the values of probability from the forecast and observed frequency, right? So whenever, if you look, whenever this diagram, the probability give the 80% of an incident, but it's actually in history, it happens around 65%. That means you are overconfident of your forecast. So you're giving like 80% times, let's say these things happen, but in observation, it's happened only 65%. Same thing with the other way for the underconfidence. Like, for example, you are giving only 60% for an incident, but actually it's happened more than 80%. So from this diagram, we can actually conclude whether our focus system is like overconfident or underconfident or perfect. We can also like, in terms of because the resolution is also a big thing, and the sharpness. So that is why, like, again, a little bit of more example. Like if you look the first example, it's look like perfect reliable, right? Because it's actually on the 45-degree. And if you look on the sharpness or the resolution concept, the probability is either 0 or 100%. So it's a perfect resolution and perfect sharpness. In the middle is a perfect reliability, but very poor sharpness. So that means, like, for example, if you have, suppose you're always giving a probability around 30 to 40%, or, or that kind of things, you may have lots of data on that particular point. So you can plot it, you look like reliable, but it don't have the sharpness. The third one is like perfect sharpness, but poor reliability. So it's not like every time we really need a sharpness. We need a sharp focus, but it should also have a reliability. Otherwise, like your forecast giving very false kind of alarm every time. Like for example, you have a weather forecast models always give like 80% chance of drought, 90% chance of flood. But in general, like if you go back and calculate the observed frequency, it doesn't happen. That means your forecast is always giving a very strong probability or sub probability, but they don't have the reliable. So both the term is so important, reliability and resolution, and the sharpness together to take a decision whether this system is perfect or good. Now, again, a little bit of sharpness. I just put the slide for the reference, like how it looks like. For example, this is, again, 0 to 100% beans, and you can look that this particular system has more forecast in that, less than like 0 to 20%. That means a sharp in the lower or the lower tail of the distribution, not much on the other things. And you can also have a different kind of repeating things, but I just want to give those things for future reference. Like you can actually have a different kind of sharpness from the focus. Now, the reliability diagram actually what gives us, like it's actually a graphical representation of bias scores, and is actually, we need a large samples to calculate the bins. Now, go back to again that we calculate the bias score for each category or each incident. Suppose you have a multi-category forecast, like 5 category, 6 category. So on that note, you have to calculate the bias score independently. So how to take the decision? So, or sometimes it's tedious. So it's better to calculate or accumulate all those categories and calculate one score. That's called rank probability skill score. It's actually same like, mean square error, but actually kind of cumulative way to represent that square error. Again, like from the RPS, we can also calculate the RPSs, which is 1 minus forecast and the reference, the way bias score represent exactly same. Now the question is like, there's another concept called continuous rank probability scores. So for example, you suppose you only give the forecast for 3 category, like 33 less than 33, between 67 and more than 67. So for in previous example, you can actually calculate or accumulate this 3 category and calculate this thing in a summation way. But what about you want to calculate for whole distribution itself? Let's say if you look this particular, if you can look my cursor, like where is the forecast PDF and observed PDF. Suppose this is our forecast PDF, which is, red line, and the observation happened somewhere in 60 to 65. If we convert it in the cumulative density function, the observed CTF look like a step function. That means it's either 0 or no 1, right? Because you don't have in between the values, but in forecast we have in between values. Now the question is, can we calculate the area of the difference? And obviously, like, if you have the forecast is very sharp and, reliable, your CDF also look like very, close to the step function. But for example, this is a one example look likes, and we can calculate instead of, summation of each category, because we are interested in the area. So we have to go through like using the integration. So that's called continuous rank probability score, like same concept, but in a, continuous scales. Again, like it can also like convert to the skill score, using a kind of ratio. Another concept on that direction called logarithm skill score. So the difference between RPS and the logarithm, like the logarithm skill score doesn't depend on the forecast probability of the other categories. So this probability means like it's local than the RPS. So RPS need this cumulative weight to calculate different category, but logarithm is kind of independent. But instead of calculating the forecast skill, it's actually taking the log of that probability and calculating the same way. It has like, it's not too much, kind of, I can say not popular, but it has its, pros and cons. But I think like if it's always good to have a log P, and, in my next discussion, when I discussing about the ignorance score, I will elaborate this concept, like why we need the log to actually have the verification. So that will be the last day of my discussion, like where you can do it. I just put this slide here to have an like idea, like from where this logarithm skill score comes is actually from the same family of RPSs, but instead of the already the forecast is just log. Now, if we just recap a little bit, because it's so much and I just go so quick, I understand, but it's time is constant. But if we just, just recap like what we do up to now, we are actually using two different approach. One is like kind of consistency approach, like does the observation statistically belong the same distribution? So we use ranked histogram, we use signal to noise ratio, we use signal to total ratio. That one concept. Another concept, like, kind of a concept of reliability, sharpness, resolution, and skill. The reliability, sharpness, and resolution can be actually calculated by the Bayes score, or it can actually uh, plot in a figure using reliability or attribute diagram. And the skill score is like kind of same idea, but you can actually compare a different forecast or different reference. So up to now, we are thinking about that. The last one I just want to mention very quick, which is a discrimination. The discrimination means like when, like if the event Y occurred, what was the forecast of X? So that means like, suppose if you look in this particular PDF example, like the blue one is like distribution of the deterministic forecast when the observation less than 25 degrees Celsius. And the distribution of the red is actually when the observation greater than 25 degrees Celsius. So whether in our forecast system, the forecast system like kind of able to discriminate between two different systems. So that's also another measure. And using the relative operating characteristic, we can actually plot it. So in short, it's called ROC, but we can calculate the ROC, the things. But the interesting thing is, okay, so before explaining how we calculate the ROC, like here's some example, like how the discrimination of look like. This is a example like we actually show last slide, like a good discrimination, like event and non-event. But if you look in the middle, it it's kind of very confusing, because some of the area, like you see that the intersection part between two PDFs so more, like you can't even actually discriminate properly. Another example, but with a different kind of standard deviation, but again it's good discrimination. Now comes to the point like how we can calculate the discrimination or how we calculate the ROC is again a very, we already saw those example, the slide from morning onwards, like we are using the 2 by 2 contingency table. Here the difference is like, kind of yes, no focus, but we also add the probability itself. So what is the event of the probability? What is the probability of forecast occurrence? We can calculate the same way, but in terms of probability, you can calculate the hit rate. That means like, your probability is right direction wherever the observation happened. In that sense, you can also calculate the false alarm rate and false alarm ratio. So based on those contingency table, somebody can actually recreate a plot like this. But just to make sure that the difference between attribute and this diagram. So in attribute diagram, reliability diagram, we are always talking about like how close is our line to the diagonal, and if it is close is better. But it's totally different here in the ROC, because it should be differ. And because the x-axis false alarm, y-axis that hit rate or probability of detection, so your probability of detection should be more than your false alarm. And if something actually happened in the diagonal, that means the same, like this forecast has the same false alarm rate and the hit rate. That means like your forecast doesn't have the ability to discriminate between event. So it's a total different way, but look like same. And we mostly interested to calculate like how far this diagram goes from this diagonal and how close it is to this one. It's look like kind of a step function, but in a different way. Just giving one example, in a probabilistic concept, how somebody can calculate those hit and false rate. Again, we can actually calculate how many times it happens when you give the 80% to 100%, 60 to 80, like different beans of probability. You can actually calculate how many times it happens, and you can simply plot it. It's like a kind of a scatter plot, like between the, if you calculate the false alarm rate and hit rate. These are like 2-3 different examples. Like let's start with the middle one. As I explained already, like if it is look like this, that means it has an equal chance. So the area under the curve is kind of 50%, because this line is also like, if you're thinking about 100% of the square, like it's actually divided in a symmetric way. But if you look the right side, this plot, it actually cover 100%, because it look like totally a kind of a step line, which is actually covered total area. In general, we caught this kind of things like, perfect forecast, obviously 100%, but if we don't have perfect, but still if we have a forecast which an area under curve is more than 50%, it also like considered as a good score. So now question is like, in terms of grid point wise things, can we plot those things in grid point? It's very tough because if you have like 300 grid point, like you should have a 300 ROCs. But on that note, in like instead of calculating and plotting the ROC, you can calculate the skill score, which is again is a representation of the area. So it's kind of 2 into area minus 1. So you can calculate this skill score for each grid. And if it is greater than 50%, you can say like my forecast has that ability to discriminate between event or non-event. That's a one example. The reason behind I put this slide because ROC is again same as Brier score. It can calculate for each event. Here in the seasonal time scale, ROC can calculate below normal, near normal, above normal. It can be calculated greater than some threshold or not. But if you look this example, you can see like this forecast has more ability to discriminate when the event come in the below normal category, but not as much as the near normal because it's actually poorer than the 50%. So it's actually, if you look for this forecast, obviously it's not that much of good for the two different category, but it's good for the one category. Is there any way we can actually combine like RPSS, this ROC? The answer is yes. You can actually combine this ROC for different categories or different threshold, and it's called generalized ROC. And again, we can plot the general ROC for each grid. You can actually calculate those generalized ROC skill score for each grid, and you can plot that combining all the different categories. I think almost end of my talk. So instead of putting a different summary, I just want to like put some of the bullets. You may think about like why we need so many different kind of scores. Why not just 2 or 1? The answer is like we need a different score because we need to measure different characteristics. Some scores give us the accuracy, like how, like whether you capture the probability of incident happen or not. Some skill score giving us the idea about like whether my forecast has a discriminancy between the event happen or not. So it's a different dimension to look the forecast. So that's why we need a different kind of skill score. And also it's very important to choose the different skill score based on like the different behavior, right? Or you can say like, to understand the different behavior of the forecast system, we choose the right forecast skill score. Again, like if you're thinking about whether you are thinking about like to find it out the signal to noise ratio, to find it out like whether the mean of the system is close to the other members, then you have to go, signal to noise or that area signal to total ratio. If you're thinking about, no, I'm just thinking about whether the forecast is sharp or not, or it has a resolution or it has a reliability, then you go to the attribute diagram. So it has a different, that's why like we need a different kind of scores to actually quantify the different behavior of the forecast. On that note, I said thank you very much, and I think maybe I just update this slide and putting more reference, and I already put anything GitHub, but I can upload and update the slide. Thank you.
Thank you, Nachi.
Yeah, just stop sharing.
It was it's difficult to compress in 1 hour so much information. I'll let actually Ian sharing the question.
Okay. Yeah, I see we have one message in the chat, which is actually multiple messages within one. From Faith. At what level can you say a forecast is reliable while using the resolution, reliability, sharpness, and Brier scores? Do you have to balance the scores from all these attributes? How close should the line be to the diagonal within the reliability diagram? Is there a range for these scores? So I think that's 4 question marks in there.
Yeah, obviously there is a range of its scores, and maybe it's better again share the screen. If you look, this diagram is like, it's actually explain this, the balance between the reliability, resolution, and sharpness. So not necessarily we should have a kind of 45-degree lines. If you look this area, if your lines falls between those area, it can be also considered as a good focused, because we need a balance, right? Because it's kind of, again, this example, if you look the first and last, in both the cases the sharpness is high, uh, uh, but the last one is a poor reliability. So whether you go choose from this or that, or you go through the middle, so it all depends on the system. But again, we may not have perfect diagonal line, then we can find it out whether that line falls between this area. And obviously each and every skill score has a kind of limit, whether it should be minus infinity to plus one for the prior skill score case. So we can actually find it out from there. So it's always like, in practical, it's always hard to balance these things depending on which scale you're talking about. If it is seasonal focus, it's extremely tough because the probability mostly come very, less sharp probability. So, but again, if it's weather focus, you may have the sharp focused. Okay, is there any other?
There's one from Cynthia. So, great presentation. How can I do, or which statistics can I use in order to measure the advantages of a high resolution ensemble versus a coarser one? I understand that I can explore their attributes separately to look at the characteristics.
Yeah, I think like you already mentioned the answer. So yeah, like if you wanted to find out like high resolution and low resolution, you can calculate the kind of signal to noise ratio. You can calculate those bar diagram of each bins of probability using like Talagrand, those kind of things. But Ian, you like, if you have any other answers, you can also like update these questions. But I think like this is again like the attribute diagram is the best to find out between different resolution of the ensembles.
Okay, there's a follow-up from Faith. You've mentioned the need to look at a large number of forecast observations. I think the word large is relative. Can you explain a bit on what a large size would be in your case from your experience? And thank you for your elaborative answer on the reliability diagram.
Yeah, that's a really good comments. Again, it's a very relative for the large scale, but what I have my own experience is seasonal and subseasonal scales, mostly seasonal scale, where we have a very less number of data set. So for example, we have, let's say like 40 cross 60 grids and let's say 30 years. So if I go with every grid and calculate those skill scores, especially the reliability or the rank histogram, I only have a 30 samples, right? But instead of that, if I just club all those grid together, then I have more samples. So on that note, I can say like if you compare a one diagram which is based on 30 and one diagram which is based on 30 into 40 into 60, that give me more confident because it has more incidents. And obviously those diagrams, reliability or rank histogram is not actually giving you an idea about the spatial scale. It's giving you an idea like whole distribution or whole forecast system. So it's again, if you have more data set, you have more confident of your skill. If you're less data set, it might be, it's a randomly happen for that only that 30 case. It's like, again, go back to that significance test concept, like whether, like that's what like Ian explained the bootstrapping thing. Sometimes people do the bootstrap to have more samples because you have to, take the decision based on those skill scores, and that decision should not be sensitive to the random chances.
Thank you. There's one more just come in from South Africa, Stephen. Good presentation. How important is the hindcast reforecast period in calculating skill metrics and scores? Some models have long climatology and some not.
Yeah, it's kind of follow up the same thing. Like that means you're thinking about the samples, like how many samples you want. So it's again, it depends on if some hindcast have, some model has 30 years of hindcast or 40 years of hindcast. You don't have control on that. You have to use all. There is no basically, I can say like, oh, we need a 70 years or 80 years, because it doesn't matter what we say. Like it matters like what we have, because mostly the seasonal scale or subseasonal scale, we have the reforecast hindcast concept where they run for a particular time period because it's computationally very expensive. But in that case, again, resampling in one of the idea that you can actually resample using bootstrapping or some other resampling technique to find out that confidence interval, or again, p-value if you're thinking about to show the things. But you need more samples, obviously.
Yeah. I think that's probably all there is in the chat. There's a link there, but I'm not sure what that's to do with.
Yeah, thanks from Raghu. Again, I'm kind of very apologized because so many different concepts and I have to just run in an hour. And it took me a lot to understand each and every concept, because it's obviously different, concept for every focus system. So I will update this slide and putting more references and put it in a GitHub. You can find it those references.
Right. Yeah.
Maybe Raghu can explain his link.
Yes. Dr. Raghu?
Yeah, thank you. Without taking much time, I would like to just draw your attention. This is a very good link from Tiggy Museum, where the users can actually have a feel of number of samples. If you go to that link, the students can go to that link. Okay, yeah, fine, great.
Yeah,
here it is showing the verification from all the models here, different models, as you can see. And on the left side is the observed frequency, and the bottom axis, x-axis, is the forecast probabilities. Okay, and the verification is based on, as you can see here, each and every point has a different color, right? So for lower probabilities and all, the sample size is really, really big, 10 to the power 5, 10 to the power 6, as high as 10 to the power 8. So this verification is based on a very large sample starting from 2007 to 2013. So this is the kind of like large sample it takes to get a robust statistic, and that too for lower probabilities. As you go to higher probabilities, again, you can see it's like as the sample size is going down, and some of the models, even the ECMWF model, like for example, the panel Q, you can clearly see it at higher probabilities, the forecast skill is it's becoming like poor. So this is what happens. So large, as long as you have large samples, you still get very good reliability. And on the red dots, you can all see in almost all the models are very close to the diagonal. Yeah, just to highlight the sample size and its relevance, it's very clearly, nicely shown in this particular example.
That's a really good one. And I believe it's like the probability of precipitation exceeding 90%. So it makes sense. Like they have a very, if you look the probability, it makes sense to have the less numbers, because the probability of that 90th percentile should not be more. Yeah,
correct.
That's a good one. Thank you, Dr. Raghu, to share it.
Yeah, thanks.
Thank you for that.
I see.
Karen has his hand up.
I was wondering, the reliability plots that we just saw, none of them had intervals on them. I wonder if one can turn that into an exercise for the students Barbara showed examples of reliability plots with intervals, confidence intervals, any kind of interval. I wonder if some students should just take it upon themselves to go update that figure, improve them by putting some sort of an interval on them.
And then you'll have a job.
Oh,
I
yeah.
think that is why that the bootstrapping is so important, right? To have this confidence sample for every cases. Okay.
Okay. Looks like we might have come to the end of the discussion. Thank you for a great talk, which inspired a lot of really interesting questions, and you gave some good answers. I don't know if Barbara or Ted want to say anything about tomorrow before we close up for the day.
Go ahead, Barbara.
Yes, so we're going to have a drop-in session at 10 BST with me and Ian. And then we'll have a little bit of a pause so people can work on the assignments or on the project in the case of the people that are working on the group projects. And so this is all for now. There is another drop-in sessions tomorrow at 1400 BST, and then to other lectures. This was a very full day, so there is a lot to take in. The slides are on the GitHub, and we're going to try to make available as soon as possible also the recordings of the lectures. That's all I had to say. Anything else, Ted?
No, that's it for me. That's great. Yeah.
Good. So thank you, everybody. Thank you, Ian, and thank you, Nachi, for the presentations. And good. Well, we'll see you tomorrow.